I just started. Just started. So you're free and clear for all your weird comments. All right. In 15.3, we're going to be talking about logarithmic equations. So we'll just start with a little definition. Our definition simply states that a logarithm is basically, or a logarithmic equation is equivalent to the exponential equation b to the y equals x. That's equivalent to saying log base b of x is equal to y. So what this is saying is, like, if I want the question, what power of 2 is like equal to 3? The answer to that is like log base 2 of 3. This logarithm is basically telling us what exponent is the answer to this equation, right? It's kind of the idea there. So let's do a couple of examples on doing that. So here's a bunch of logarithmic expressions. We're just going to try to evaluate these guys. So I'm going to just start by writing it equal to y. And then I'm going to use that definition for a logarithm. So it says that log base b of x is equal to y. That's equivalent to saying b to the y is equal to x. Oops. So if I look at this, 4 to the y equals 16. What power of 4 is equal to 16? 2, right? Dunzos. Easy peasy. So here we have log base 5 of the square root of 5. Again, I'm going to write that equal to y. So I do log base b of y is equal to x. So what power of 5 is equal to the square root of 5? 1/2. Remember that radical is the same thing as a fractional exponent. Bless you, bless you. Remember that rule for exponents there? That a radical, like the nth root of a, is a to the 1 over n. Let's see. We have log of 3 is, or log base 3 of 127. So again, that's 3 to the y equals 1 over 27. Well, there it's a little bit harder to see what power of 3 is 1 over 27. But I notice that 27 is 3 to the 3rd. And if I have 1 over something, I can rewrite that with a negative exponent. So what does y have to be then? It was just -3, man. You're back. That was so fast. Very good, sir.
Thank you.
You're welcome. So I have that other rule for exponents that we used. Log base 12 of 1. So again, 12 to the y is equal to 1. Well, what does y have to be there? What power of 12 is equal to 1? 0! Yeah, remember a to the 0 is equal to 1, provided that a is non-zero. What is 0 to the 0 as an aside? Undefined. 0 to the 0 is undefined. Correct. E was log base 8 of 8. So again, I'll write that equal to y. That means 8 to the y is equal to 8. Well, what's y have to be then? This is the easiest one. 1, yeah, good job. He was pointing. He was busy drinking his juice. All right. So just to reiterate here from these examples, we can make a couple of observations. So from example D, we can say that any log of 1 is 0. From example E, we can say that log base b of b is always going to be 1. Now for these last two, remember that we have these two equations. No, that's not right. It's y is here, and that's x. Okay, that's better. So if I take my value for x and I plug it in there, we can say that, right? What's that really implying, though? That log base b is canceling exponent base b, because I know y is equal to y, right? Now, what if we go, and that's what we're seeing here. What if we go the other way and we take the y and plug it in? There we have b to the log base b of x is equal to x. Again, so that would be saying that, like, oops, let's write x equals. Those guys are canceling the exponent base b and the log base b, not y, giving me x. So that's what we're seeing in those last two properties, is that logarithms cancel exponent bases and exponent bases cancel logarithms. Of everything we're going to do in chapter 15, that idea right there is the most important one. Almost everything we're going to do, if you understand that rule well, you're going to be in okay shape throughout everything we're doing in chapter 15. That logarithms cancel exponent bases, and then exponent bases cancel out logarithms. Now, you see that when we write this, we're always writing log base b. B can be any number that's not, or any positive number that's not 1. However, there are two specific values of b that are special, that we use all the time, that are going to get a special notation and a special, like, symbol associated with that notation. So the first value of b is 10. We call 10, or log base 10, the common logarithm. And instead of writing log base 10, we just write log, and we don't write the base. So if you just see regular log on your sheet of paper with no base, it means it's base 10. And we do this all the time in mathematics, right? like when we write the square root, we don't put the 2 in the check mark like we do for a cube root, because we understand that if we don't write a 2, there's a 2 there. Same idea here. If we don't write a 10, we just understand that there's a 10 there. The other is the natural logarithm. The natural logarithm is log base e, and the symbol we write for the natural logarithm is the letters ln. So if you see the letters ln, that means log base e. Remember, e was that number we talked about last lesson, that like 2.7 yada yada yada. All right, so just a couple of examples working with these notations. So the first one, a equals log of 1,000. Now I'm going to approach this a little bit differently than we did the first time through, because I want to take advantage of this idea that we highlighted above, that exponents cancel logarithms and logarithms cancel exponents. So I recognize that this log is really log base 10. So I'm going to try to rewrite 1,000 as a base 10 number. 1,000 is 10 to what power? Third, right? Log base 10 cancels exponent base 10. So that should just be 3. Still kind of the same thing that we were doing before, but we're just using a little bit different notation to express it. I think the notation we're using here makes everything a little bit more intuitive. So again, we have log of the 5th root of 10. I recognize that log means log base 10, so I'm going to write the 5th root of 10 as a power of 10. Well, the 5th root of 10 is 10 to the 1/5. There's that. Again, I recognize I have regular logs, so that's log base 10. Now I want to rewrite 0.01. Maybe I'm going to try to write that as a fraction. What fraction is 0.01? 1 out of 100. Yeah. And now if I want to rewrite 1 out of 100 as a power of 10, maybe I recognize 100 is 10 squared. And then 1 over 10 squared is 10 to the negative 2. So we end up with negative 2. Yes, sir. Yes, sir. So the next one we have e to the natural log of 5. Remember that ln means log base e. And I know exponent base e cancels log base e. So this is just 5. Now here I have 2 equals log of x. Again, I see log. I know that means log base 10. So what do I need to do to get the x by itself? How do I cancel that log base 10? What do I have to do to both sides? Not multiplying. Not dividing. Not adding. Not subtracting. Not factoring. I need to use the exponent base of 10. So that means I'm going to have 10 to the second on the right-hand side and 10 to the log 10 of x on the right-hand side. Exponent base 10 cancels with log base 10. So I end up with x equals 100. Now, when I write that exponent base 10, notice I wrote that absurdly large. I really want to emphasize that I am not multiplying by 10, right? 10 times log of x is just 10 times log x. If we have 10 to the power log x, that's what we need. That's the canceling. Everybody's good? Okay. And the last one we have ln y equals 5. Again, whenever I see natural log, I know that that is log base e. So what do I need to both sides to cancel that log base e? I use exponent base e. So y equals e to the fifth. You could type that in your calculator and get a decimal if you wanted to, but like, pass on that. I'm just going to write it as e to the fifth. So far, so good. Okay. I want to circle back to something we did just a moment ago. Oops. So when you look at this process that we did here, this should remind you of something we did in first semester. In fact, something we did the first chapter of first semester. Oh, Boise, Mr. Kulik, that was a long time ago. Does anybody recognize what we really did there? We really did the composition of the two functions. What does this tell us if I do the composition both ways and we get x? It says that these two guys are inverses. So if logarithmic functions and exponential functions are inverses, that means every property of exponents should have a corresponding property of logarithms, and vice versa. You should be able to walk back and forth between the rules for one to get to the rules of the other. As a result, we can find the following properties of logarithms. So the first one is called the product property. So this is based on this property of exponents, where multiplication outside the exponent becomes addition inside. The reverse would be true for logarithms. Multiplication inside turns into addition outside. But the same idea. So the next one is based on the quotient property of exponents, that division outside of the exponents turns into subtraction inside. The reverse is true. Division inside turns into subtraction outside. Property 3 is based on this power of a power property, but it's a little bit harder to see how that one churns out, but I promise you that's the trick. And this last one, this change of base formula, is one that Mr. Kulik as a student used a ton of. You guys will probably never use. The difference being is the technology that we had available to us. When I was a student sitting where you are sitting right now, we did not have a calculator that could do log base 2 of 3 on it. So what Mr. Kulik would have to do is he'd use the change of base formula to rewrite that as like the natural log of 3 over the natural log of 2. In the back of his textbook would then be a table of values for logarithms. I'd look up off the table what the natural log of 3 is, some decimal, and look up off the table what the natural log of 2 is, some decimal, and then I do that decimal divided by that decimal in the calculator and press enter. What will you do? You'll take your calculator, you'll press the math button, you'll scroll all the way down till you get to the log base command, and then you can just type it into your calculator exactly like it looks like on your sheet of paper. Woo! Note that if I do the change of base formula, and I do like the natural log of 3 divided by the natural log of 2, I do get the exact same decimal. But really, folks, how would you do something like this? Use the log base button from your calculator, and you can just type it in exactly like it looks, and it's no big deal. So the change of base formulas went from something that was extremely valuable as a high school student to something of negligible value as a high school student because of the incredible power you wield in the palm of your hand. That graphing calculator is just like a remarkable piece of technology that Mr. Kulik, as a 16 or 17-year-old, would have been really excited about how much easier that made his life. All right. Actually, I don't want to do that yet. So, one of the main problem types that we'll be using that we'll be doing now that we have these properties of logarithms are going to be expanding problems. So the idea with expanding is we're going to take one logarithm and turn it into the sum or difference of many logarithms. Doing that, we're going to be doing the quotient property first, product property next, and power property last, unless there's some sort of like parentheses that would imply, no, you need to do some different order. The other type of problem we'll have is condensing. So for condensing, we're going to take the sum or difference of many logs and try to turn them into a single logarithm. To do that, we're going to be using the opposite order, power, product, quotient. Again, unless there's some set of parentheses that implies that I need to do some other different kind of order there. Yes, Kate? Sure. All right. Now I'm ready for that example that I had. All right. Let's see here. It says, assume that all values are positive. Expand the following logarithmic expressions using the properties of logarithms. So the first thing I look for when expanding is a quotient property. So I look inside my logarithm. Do I see any division in there? Nope. No quotient property. Okay. Next thing I look for is product property. Do I see any multiplication in there? Yes. Between the 4 and the x, I know is some multiplication. I don't write the multiplication symbol, but I still know it's there. So I apply the property or the product property of logarithms to rewrite that multiplication inside the logarithm as addition outside the logarithms. The next thing I'm going to do is I look inside of each of my logarithms for a power property. Do we see any power properties? At first glance, you would say no, right? Because I have just like nothing has an exponent stuck on it other than 1, which is trivial, like we don't care about 1. But look at that 4 again. What can I do with 4? I can write it as 2 squared. Now I have a power property. Oh, Mr. Kulik, are you going to do sneaky stuff like that to me? Yes, I will, guaranteed. Sneaky jerk right here. So the power property says I'm going to take the exponent. That's going to become a coefficient in front of my logarithm. The base of the exponent stays inside. And then we couldn't do anything to log base 3 of x, so that just stays the same. So that's our final answer. Okay. Moving on to the next problem. First thing I do is look for a quotient property. Don't see any of those. No division in there. Next thing I'm going to do is look for product properties. Do I see any of those? Yes. How many? Should be 2. because I have a multiplication symbol between the 3 and the a, and another one in between the a and the b to the 5th. So 2 product properties, 1 for each of the multiplications. I just do them all at once. That's just going to give me log 3 plus log a plus log b to the 5th. Everybody's good? Now, inside of each of these logarithms, I'm going to look for power properties. 3, well, that's prime, can't do anything to that. X, no exponent on that, can't do anything to that. I'm sorry, a. And then b to the 5th, that we can do. So again, the power on the exponent is going to become the coefficient on our logarithm, and the base stays the same. So that's our final answer. Everybody good? All right, last example. We have the natural log of 2x over square root x cubed minus 5. Any quotient property in there? You betcha, right? The fraction is division. So when I do the quotient property, again, I have natural log of the numerator minus natural log of the denominator. Everybody's good there? Now I look inside each of the logarithms. Do we see any product properties? I see 1 between the 2 and the x. So I can write that as natural log 2 plus natural log x, and then the last logarithm stays the same. Yes, sir. Final step, going to look again for power properties. Do we see any power properties in any of these logarithms? Nothing in the natural log of 2. Nothing on the natural log of x. What about the natural log of square root x minus, or x cubed minus 3? Is there a power property there? Yes. What is the power? Not 3. I'm asking intentionally because this is an easy place to make a mistake. 0? Not 0. What is, so square root of x cubed minus 5 means that, right? X cubed minus 5 all to the 1/2. So what is the power property? It's 1/2. Is everybody okay there? Important question. Why can't I do a power property on the x cubed? Seems like I should, right? It's because I don't have the entire thing to the 3rd power. If I had the entire quantity to the 3rd power, then I could use the power property. As it's currently written, I have x to the 3rd, and I have a plus or minus something else. No power property there. Is everybody okay with why that doesn't get 1? Has to be a single thing to that power. I can't have something to a power plus something else. No! Cool? Okay. Next ones, we're going to do some condensing. Can I know that? Yes. All right. Bless you. You're welcome. Condensing time. So the order for condensing is reversed. Instead of going for expanding, we went quotient power or quotient product power. For condensing, we're going to go power product quotient. And before, in expanding, we looked inside the logarithm for the property. Now for condensing, we're going to be looking outside the logarithm for the property. So the first thing I look for is power properties. When I look for power properties, I'm looking for coefficients outside the logarithm. I see two of them. Everybody okay? Next thing I look for is product properties. For product property, I'm going to be looking for addition outside of the logarithms. Well, I see right there. So I apply my product property. Everybody okay there? Last thing I look for is quotient property. That's going to be division or subtraction outside of the logarithm. I see subtraction right there, but wait! It's not actually a quotient property. Why not? Even though I have subtraction going on between two logarithms, why can I not apply the quotient property here? Look at the bases on the logarithms. They do not match. To use a product or quotient property, the bases must be the same. So this is as far as you could go. Oh, Mr. Kulik, that's so tricky. Well, I'm showing you all the good tricks now, so hopefully I don't fool you later. Part B. All right, we start with power properties. How many do you see? 1, 2, 3 power properties. Now, I've made a mistake with what I wrote. I made this mistake intentionally because I will guess the majority of students, if not more, or closer to all students, would make this exact same mistake that I've just made. I'm doing this intentionally. Where is the mistake in what I've written? You can always tell it's a good question when it takes this long. Nobody sees it right away. So it's happening here. That's correct. How do I fix it? Good. So either I can put a to the third, or I could write it as the quantity ab to the third. But yes, very good. Everybody's good with that? Okay. The next step is I look for product properties. Do we see a product property here? This is another good question because this is something I guarantee we can make a mistake on again. Is there a product property? Yes, because I have the addition. What two logs do I need to combine into the product property? Yes, very good. Why can't I combine the middle and the last where it looks like the addition is? Not because of the number of variables. If we go back and we look at the property, the sign on both the logarithms has to be 1. They have to have coefficient +1 in order to go together. If I look down here, the one with the subtraction symbol in front really has a coefficient of -1. Can't use that in a product property. Now I can use my quotient property. Again, the part with this -1 coefficient has to be the denominator. What do you notice about this fraction, though? Natural log a to the 4th over b squared, or times b squared over a cubed minus, or times b cubed. What can I do with that fraction? Reduce! Right? I can reduce that fraction, end up with just a over b, or natural log of a over b. And skip that. Okay. All right, in 15.4, we're not going to see any new content. All we're going to do is kind of apply the stuff we've talked about so far. Really what we're going to be doing is solving equations. So I'm just going to give us some examples of equations to solve, kind of walk through what we do to solve them, and then we're out. Now remember, in general, to solve things, we start with like the reverse order of operations, right? We're undoing simplification. So the first thing we'd want to start by doing is undoing any addition or subtraction. Now the only addition and subtraction I see is going on in the exponent. I can't really undo that addition and subtraction until I've gotten the stuff out of the exponent. So I'm going to leave that for later. Next thing I would want to do is undo any multiplication or division. I see I do have some multiplication going on between the 14 and the 1/3 to the x minus 1. So I'm just going to divide both sides by 14 to start. 126 divided by 14 is 9. Now, what I need to do next is I need to get rid of that exponent base of 1/3. What do I need to do to both sides to cancel out that exponent base of 1/3? I'll give you a hint. It starts with an L. Starts LO. You need to use a logarithm. Great. Any logarithm will work, but to make this process as efficient as possible, which base should I choose on my logarithm? What should be the base that I choose on my logarithm? So I'm trying to cancel this guy out. Yes, the base of my logarithm should match the base of my exponential. Because exponent base 1 or log base 1/3 cancels exponent base 1/3. So then I just add 1 to both sides. And it's calculator time. So I pull up my calculator, I do math. Scroll to the bottom, pick the log base command, type 1/3 into the base, type 9 into the argument, and then have my +1, and I get -1. So far, so good? Next example. What should I do first to solve 12 times 3 over 2 to the x over 5 equals 27? What should I do first? Who can tell me? What should I do first? Great, divide both sides by 12. When I do that, 27 over 12 reduces to 9 over 4. Next, what do I do? What do I do next? Excellent. I use a logarithm. What should the base of this logarithm be? 3 over 2, the same as the base for my exponential. Very good. And log base 3 over 2 cancels exponent base 3 over 2, so I'm left with x over 5 equals log base 3 over 2 of 9/4. Then I just multiply both sides by 5. And then into my calculator she goes. When I do that, I get 10. One more exponential equation example. This is the most difficult kind of solving or exponential equation solving problem you'll see. Looking at this problem, what makes it fundamentally different than the previous problems you've seen? Not the fraction. I have x's in 2 different exponents. That's going to be the issue. So we'll start by come on. Nobody wants to do this. Start by multiplying both sides by 4 to nix the fraction. Everybody good there? Next thing I want to do is I don't like that negative exponent on the, well, here's the first question. Can I add 3 to the x plus 3 to the negative x? 3 to the x plus 3 to the negative x. What's that get me? You can't add them, guys. It's a trick question, right? To add 2 things, they must be identical. Right? Like you can add x and another x, but you can't add like x to the first and x to the second. The exponents are different. Same idea here. Okay. So I want to get rid of this x, or 3 to the negative x. Here's the best way to do that. I'm going to multiply both sides by 3 to the x. Why 3 to the x? What do I get when I multiply 3 to the x by 3 to the negative x? I get 3 to the x plus negative x. Remember, we add the exponents when you multiply 2 things together. When I multiply 3 to the x times 3 to the x, I get 3 to the x squared. What is x plus negative x? 0. What's 3 to the 0? 1. Look at this equation for a moment and tell me what type of an equation we have here. Nobody sees it. Let me give you a hint. What if I replace the 3 to the x's with y's? What type of equation do we have here? A starts with a Q. Quadratic, right? You see the variable squared? To solve a quadratic, it's got to equal 0. So we'll subtract the 8y over. Now to solve this, I can either factor. Well, there aren't two things that multiply to give me 1 and add to give me -8. So that means I'll do the quadratic formula. So y equals -b plus or minus b squared minus 4ac all over 2a. -8 squared is 64, minus 4 is 60. Am I done? No. What do I still need to do? That's not the issue. What variable did we just solve for? Y. What variable should we be solving for in our problem? X. So guess what I have to do? Yeah. I have to plug in 3 to the x for my y. So I do that. How do I get rid of that exponent base 3? What's going to get rid of that exponent base 3? A logarithm! Which logarithm? Log base 3. Notice this is why I didn't worry about simplifying, because I knew I wasn't done. I still had a lot more to do. Now this is going to go into the calculator. And it's just going to give me some stinky decimal, so that's why I'm not going to worry about simplifying the radical, because it was not going to be my final answer anyways. So you could simplify the radical. So I get 1.88. And then if I do the subtraction, I get negative 1.88. Everybody cool? That's the hardest kind, is where you have the exponential nested inside of a quadratic like that. Those are the worst ones. Let's do some logarithmics. I have 2 logarithmic equations for you guys to solve. And then we can be done for today. All right, first equation. 3 times log of x squared equals 6. First thing I should do is, what's up? No, that's 3 times. That's a multiplication symbol in between the 3 and the log. Divide by 3. So then we have log of x squared is equal to 2. Now we can start attacking that, getting rid of that log. How am I going to get rid of that log in front of the x squared? How am I going to get rid of that log in front of the x squared? Well, remind me, what's the base for that logarithm? 10. What cancels out a logarithm? An exponent base, yeah. So we'll use exponent base 10 to both sides. So x squared is equal to 10 squared. So x is going to be plus or minus 10. Everybody's cool? We're not done. All exponential equations must be checked for extraneous solutions. To do that, we have to plug our answers in for x squared and make sure we get a positive number inside the logarithm. Well, 10 squared is 100. Negative 10 squared, also 100. Both of these check out. I get two answers there. Next example. Oh no! What do I do here? So those are ln's. Those are natural logs. Those are logs. So that's fine. What is fundamentally different about this problem than the previous one? I have variables in more than one logarithm. Everybody's okay with that? So my first order of business is I'm going to condense so I get a single logarithm on each side. So on the left-hand side, I see a product property. On the right-hand side, I see a power property. So I'm going to do that as starters. Everybody good? Now that I have it down to a single log on both sides, I can cancel that single logarithm. What's going to cancel out a natural log? Exponent. Base. E for natural logs. What kind of an equation am I left with here? Quadratic. So I'm going to FOIL that out. Negative 5x plus 2 equals x squared. We'll subtract the x squared from both sides because this has got to equal 0. That thing will factor, but it's going to be that long factoring process. I don't want to deal with it, so I'm just going to use the quadratic formula. Negative 5 squared is 25. 4 times 2 times 2 is 16. 25 minus 16 is 9. Square root of 9 is 3. 5 plus 3 over 4 is 2. 5 minus 3 over 4 is 1/2. But I'm not done. I have to check. If I plug 2 in, actually let's use a different color. 3 times 2 minus 2, that's positive. 2 minus 1, that's positive. 2. That's positive. That one checks out. 3 times 1/2 minus 2 is negative. Stop! Discard, it's extraneous. Only need one logarithm to fail to be positive, and I can stop. This is where I'm going to finish for today. Last time we assigned 1 through 36, right? That happened on the 21st. Today, we're assigning 37 through 130. Next time we meet, you should expect a homework quiz. That'll just really be on 15.1 and 15.2. So if you do that 1 through 36, you should be good to go. Yeah. Did you look at the homework set? How many questions are in the homework set for this chapter?
I thought it was a typo.
No, it's not. Let's go look.
Is it due this Sunday or next Sunday?
Goes to 184.
Oh, but some of them are multiple choice.
No, those are multiple parts.
Oh, great.
Is it due next Sunday?
Well, not 1 through 36, assuredly. Well, here's what I would tell you there, Hunter, is if 37 through 130 isn't due this Sunday, it'll be due next Sunday, but then there'll be more on that also. So it'll probably be like 37 to like 160 or something, which again, like pick your poison at that point. Like,
They're like easy, though. It's just like,
a lot of them are very easy.
it's just like put in your calculator and you get an answer.
Some of them are as simple as that. Seniors are done.
So we don't have to do that one?
No, you have to do the review packet.
Oh, that's it?
That's everything from here on out, unless you have like later missing things. Your assignment is the review packet. Get the packet done. I'm not asking you to do anything else. No homework quizzes, no tests, no homework. Do your packet.
Mr. Kulik, do you have a printed version of the packet, or is it all?
Yes, I do have a printed version I can hand to you right now.